All right. Well, welcome to this information session on our material science and engineering department here at UT Dallas. And so without further ado, I will just hop right in and we'll get going here. Okay. So as you saw yesterday, on Monday, hopefully you saw Dean Adams in the opening session. She's obviously our Dean of Engineering, our leadership team, so to speak, here in the Material Science and Engineering Department, at least as it relates to graduate students, is our department head, Dr. Manuel Quevedo Lopez, myself as the graduate director, and Dr. William Vandenberg, who is the associate department head. We are in the midst of starting an undergraduate program, which will kick off hopefully fall of 2026. And maybe the impact of that we can discuss later as we kind of move down the slide deck here. All right. Okay. So we have quite a few faculty here. This is our core faculty in our department with their areas of specialty. I'll save the time of going through each and every individual because we have a web page link, I think, that I made available here in this presentation that will take you to the list, as well as affiliated faculty members and other things along those lines. So with that, I'll continue on here. But in general, the one thing that you will see as we move forward through this presentation is that UT Dallas's Material Science and Engineering Department is not a traditional material science and engineering department, as you'll see here coming up. Okay. Whoops, wrong direction. Sorry. All right. So, why MSc here at UTD? We feel we have a very interdisciplinary curriculum. I mean, at its core, materials themselves involve and how we use them, right? It involves chemistry. If it's a biomaterial, it could involve biology. We'll have mechanical engineering aspects of things, electrical engineering aspects of things. And so all of that you will see on an upcoming slide is how some of this manifests itself and comes together with some of the topics that you see there in that first bullet point. We do have some definite world-class faculty here. I joined here a while back, but one of the things that I did not really realize was just how many resources we had, that we do have now, even back when I had applied to hopefully be employed here. And I was just pleasantly surprised because, we're not some big flagship, institution. However, the things we are capable of, we can do really well. Through, and as we continue on here, through the research opportunities that students have because of the interdisciplinary nature of things, the world-class faculty, the research facilities are also world-class. And so you can get access to some cutting-edge labs and collaborative research space that we have here in the building. It's the Natural Science and Engineering Research Laboratory. There's a whole little story on that, but it's over a several $100 million building that was erected to house labs and things. So there's a lot of folks in this building that do a lot of different kinds of research. I think and if we go kind of outside the university and just the holistic academic aspect of what UTD offers, I think it should not go without saying that, of course, the DFW area itself, this Dallas-Fort Worth area, is definitely recognized as a top city for just jobs, families, things to do, all of those kind of great things. And then through that, then there's an offering of strong industry connections. As you guys heard on Monday, I mean, literally the land that I'm sitting on, not you all, but the land I'm sitting was, TI's land that they donated to the UT system, and out came UT Dallas out of that. So at least my little joke is like, TI is like our grandparents and how they look after us and take care of just the campus and are willing to fund things, and they're just a good place to have and place for our students to ultimately go and work. Okay. One of the advantages again of being in this area is our high placement rate of our students and just students in general that come out of UTD, and the fact that there is a lot of industry, technology, all kind of career options in the area. Lots of entrepreneurship happens around here. There's a lot of venture capitalism in some ways too. If you have great entrepreneurial ideas and things along those lines. In fact, we've had a faculty member here who has actually been able to spin off one of his companies that was actually purchased. So it's definitely possible here, and of course the starting salaries, say with your PhD, are pretty robust for this area, because while our cost of living has kind of increased since I've been here, at least home buying has increased and things. I still think it's a really good area to live in terms of cost of living relative to other big cities and things along those lines. And there's one unique thing that we offer here at UTD in our department is a semiconductor technology graduate certificate. Now, that certificate, though, spreads across multiple majors. So you can be in electrical engineering, of course. You can be in mechanical engineering. And there's even ways for somebody even outside of engineering, like say physics, can also obtain this, and we'll talk a little bit more about that later. Okay. In addition, this is where a lot of our students get placed in employment, or they have worked here. This isn't the comprehensive list, but hopefully you see names and things that you recognize, especially at least if you are in the semiconductor microelectronics kind of area or field, and if that's your ultimate interest. But we do have students that do work in all sorts of places, other national labs here. Some people, this one that looks like a weird MEC, it's IMEC. Actually, that first little thing looks like a backwards J. It's really supposed to represent an I. That is a research consortium in Europe that we've had students even go there too to do semiconductor related types of research and things as well. So there's quite a few avenues and ways for our students to find employment here that come out of our department. Right. Um, so in terms of our research and where our core strengths are, and what this is, like I was alluding to, that kind of makes us be somewhat of a non-traditional material science department, where you may have metallurgy, ceramics, and things along those lines. We're more in the nano semiconductor space, and we're branching out, as I'll explain here in the second bullet point. But it says here we've historically focused on electronic materials and devices and the associated surface science that goes with that. And for those of you, if you're unfamiliar with microelectronics and chip fabrication and things along those lines, the layers of material are so thin that the surface can play a huge role between, say, two dissimilar materials, right? So if we're bringing these two materials together, they are supposed to have some functionality when we do bring them together. But if that surface is not pristine, or we don't understand how that interaction is occurring at that interface, it can lead to problems with the microelectronic type device we're trying to develop, or things along those lines, as well as just understanding the science. Like, the big foundries and chip manufacturers and stuff, sometimes because, time is money and they need to be shelling out wafers that have chips on them that they can go into our iPhones, our laptops, any other devices that we may have, iPads, things along those lines. We can help them understand what's going on at these interfaces, where we have the resources, the expertise, and the infrastructure to do so. But one thing that's recently happened, because of our historical focus and how well known we are in this area, we've been able to form the North Texas Semiconductor Institute. And we'll have a slide. I'll have a slide or two on this a little bit later. One of our other areas that we recently branched out into is the energy related research areas. And we've been able to strengthen this by hiring new faculty and leading the creation of what's called the Beacons Center, which stands for Battery and Energy to Advance Commercialization and National Security. This is a DARPA funded project, and I believe it was 30 or maybe $40 million that we were awarded to faculty members here to create this center. And so I'll talk a little bit about both of these here a little bit later on. But before we go there, as Dean Adams had mentioned on Monday, there are these strategic initiatives that we have here at UTD that go across all the different disciplines of engineering. We happen to be leading two of these thrusts. One is, of course, the semiconductor and technology space, and the other one is the energy science and technology. So with that, basically what it boils down to with the energy and science, at least as it stands right now, is battery technology. And how can we make better batteries that either hold more charge, last longer, have longer lifetimes when you're constantly cycling drain batteries and charging them back up? How can we make sure that we can extend the life of these batteries? So there's a lot of different things along those lines. And of course, you then see the interdisciplinary nature because we're correlating things like through pretty much every research grant we write now, we talk about incorporating or including artificial intelligence, for instance, and things along those lines. So now you can just kind of see how these different research thrusts then have all of these other aspects included in them. Okay. So there's Dean Adams has a strong team. I think that's trying to, and they work with us. They take our feedback and what we think the next thing to study is, or the next thing to conduct research on. And they definitely try to work to enable us to be able to achieve that. And we, of course, try to work towards securing external funding from various agencies, branches of the military, Department of Defense, or what have you. So there's maybe even potential more faculty going to be hired soon across all of the different disciplines, and things along those lines. So I think UTD is definitely on an incline, so to speak, in terms of growth and things. Some of our big picture things here on research expenditures and kind of where our fundings kind of come from. This is across the entire school, but in this blue region that you see here, this is our portion of this total 56 million in expenditures that we traditionally had, at least as of fiscal year 2024. Okay, so yeah, so we have to fund it because we don't have an undergraduate program. The only way we can really truly support students is to have research grants. And so that, because we don't really have like a large number of TAs because we don't have this huge undergraduate program, right? And so that's why I was alluding to earlier in the fact that in fall 2026 we will begin to open up we'll have our first cohort of students that'll be an undergraduate major. So at that point, maybe we will have a few more TA slots and things that could be really good and useful for those students who've been admitted but haven't necessarily secured some research funding through a faculty member. Right? As you mentioned earlier, these are just different, drilling down a little bit deeper into some of our key areas of research. These are some of these interfaces. If you look at this upper left figure, this is a transmission electron microscope, making like a attempt to make a gate all around sort of device. Now, of course, we're not getting all the way around under the bottom, but it's just basically trying to build devices, and then we can look at interfaces and things along those lines. So there's, of course, energy conversion, like I said before, with storage and batteries. We've got our flexible electronics that we do. There's sensors and systems that are being worked on. We've got photovoltaics and solar cell research. in a lot of areas and things. So I just recommend that if you're definitely interested, is to look at all the different faculty pages and see we usually all have some little paragraph blurb about what our research areas are and what we're investigating in things. So sometimes these things are sometimes fairly dynamic, and there might be things not listed here that you might find in their web pages. Okay. So as I discussed earlier, we have what I believe are some really world-class instrumentation, whether that's for characterization or actually creating materials and doing these things where we're integrating these materials together. So for instance, this big tool here in the middle has quite a bit of capability on it. All right. So those of us who deal with microelectronics, and like I said, we're trying to take one material and put it on top of our semiconductor wafer, our silicon wafer. This is a place where we can put the film down or begin to put the film down, but then in situ, we can take that film and move it back into the XPS system and begin to see how the initial bonding is, right? Usually what happens in a clean room or at an Intel or somewhere, Samsung, TSMC, they put down the whole film and then, begin to continue to build the device, right? So what we're able to do is, if that film was supposed to be so thick, we can stop that process and make it very thin at the surface, then go take it to that tool, and then we can begin to see what material is forming or how the bonding is occurring between the semiconductor and the layer on top, and whatever elements are in that material. We can see how they are bonding, and the way they bond can influence how robust or how pristine that interface is, or how high quality of an interface we have, for instance. So that's some of what we have going on here. We have a very good picometer resolution TEM. So of course we can see like individual atoms. So, and then there's just a whole host of all the physical characterization techniques that you would need to have: XRD, AFM, all the types of equipment you would need to be able to conduct quality research, right? We have a 6,000 square foot clean room that's equipped to handle up to like 4-inch wafers. This is, I was pleasantly surprised, like I said, when I got here, for this to be a university clean room. It's really well maintained, and they do a really good job. And what often happens is someone may recently retire from Texas Instruments, and they will have had 30 some odd years of like clean room experience or what have you before they retire. And then, they come and want to give back, and or maybe want to supplement a little bit of that retirement income with some additional funds by working here. But the one thing they do is they know how to maintain, keep this equipment going. If not, they know who to contact to get somebody in quickly to get things back up and running. And they're willing to share their wisdom with students. They do all the trainings of the students that get access to the clean room, and all of that kind of good stuff. So they have a wealth of knowledge that they always share and impart on students to make them be hopefully good process engineers, or understanding the influence of process on the science you're trying to do, because you got to be able to decouple the effects of what happens while you're making it versus what's just fundamental science, right? The influence of how you make it can influence the science. So you got to be able to decouple that. And so having wisdom in things along those lines are really instrumental. Okay. So at this point, I've been talking quite a bit about the experimental capabilities we have. And I'm an experimentalist in what I do. But we do have strong faculty clusters that do materials modeling, or say device modeling of semiconductor devices. And so some of that goes all the way down to first principle type calculations. Some of you may have heard of density functional theory, and that tries to replicate how, like I said, we might have this scenario where we're trying to look at how this film growth is happening on top of this other material, right? What's going on at that interface? Well, some of these simulations and things that they can do is also try to um, determine what kinds of things may happen at that interface. Are we going to grow a different kind of layer? Is there going to be some unique chemical composition in that region between the interface that, like I said, affects the performance or what have you? So having modeling predict that and or show that that can happen, coupled with the physical characterization methods to show that, yes, indeed, we have that kind of bonding happening at that interface. And now take that to a real world semiconductor device, right? We can demonstrate how either things need to be improved or this is what's happening. So, Intel, whoever, you know, you're going to need to be able to deal with this, or we can help you sort this out. So a lot of times we can get some industry funding to help with these kind of things, and all that kind of good stuff. But I just want to mention to any of you listening, if you're more of a computer person or like to do more simulation and modeling, and things along those lines, we have several of those faculty that you saw in that list in the previous slide. There's several of them that form our modeling group, so to speak. And like I said, they study things all the way down to how things bond to electron transport. And what we mean by that is, of course, semiconductor devices, they operate by the movement of electrons. So we've got to understand how they move through the material based on quantum mechanics and things. And so they have all these very sophisticated modeling capabilities to explore these kinds of things, right? So to get to these centers that I was referring to or talking about, um, you know, ways in which we're like leading in this electronic material space again is this North Texas Semiconductor Institute. And so we have industrial partners that form our advisory board. All of these companies you see here are local to the DFW, are local to our region, but of course have maybe international offices in places or things along those lines. And we have collaborators locally through whether it's other universities or through our community college system and things along those lines to provide resources, education, and things for those institutions or research collaborations. So as you can see down here, the center is comprised of three different areas or three types of programs. One is through our department head that I had mentioned earlier, the Center for Harsh Environment, for harsh environment semiconductors and systems. So like for here, one of the goals is to expose these devices that we may fabricate to radiation, right? The medical field obviously has a lot of instrumentation. We all should hopefully know that we literally have semiconductors in anything that's electronic today. That coffee pot that automatically knows to turn on and brew your coffee in the morning when you set the little program, there's a computer chip in there, right? That's controlling that and making that happen. So it's they're all over the place. So of course they're in medical equipment that at the same time may be at a cancer treatment facility, for instance. And so you got to deal with the radiation and how long will these things last, or these, we might work with NASA or the Air Force and things are going into space, right? So that's what the purpose of this is, or what we hope to have happen there. The workforce development aspect that we're working on, that's with like partnership through the community colleges, right? To create a pipeline so that we can have the community college students come in and then work on their 4-year degrees and then hopefully continue on to graduate school and things along those lines. And then we also want to be a facility for maybe small businesses or somebody who has an idea and wants to prototype something. That's our custom semiconductor process and device support that you see over here. And so that's kind of, it's only a couple of years old, maybe 2 to 3 years old at this point. And so it's just going to continue to grow. And funded research happens here. Some of us as faculty members are also affiliated over here. So, this is avenues for research and then maybe even potential employment with these kinds of companies here, because they will be asking us to maybe do certain things for them. And then, of course, I'm not the one that goes down in the lab and does the work. It would be you all as the students. And so it's a pathway to potential jobs and things along those lines. Now, our other center that I referred to here is the Beacons. And this is how we're trying to be effective leaders in this research space. And this Beacons is, like I said, it's the batteries and energy to advance commercialization and national security. Okay. So some of the challenges that maybe I'll just wait and go ahead when I get on to the next slide here on what those challenges are. But this is the goals of this particular center, right? One is this whole commercialization aspect and the supply chain. Okay. Prototyping new types of battery technologies or materials that are, like I said before, you're trying to either pack more charge into that same volume, so it means the battery will last longer, or that whole cycling of the battery, right? Over time, we all know that sometimes our cell phones or our laptops or different things, the batteries just don't hold their charge as good as they used to, right? And things along those lines. So that's what needs to happen. And then on top of that, just like with the previous center, there's a workforce need, right? There's not, don't have a lot of people trained in these areas to understand all the battery manufacturing, how to innovate new battery technologies and things along those lines. Because of course, a lot of these lithium ion batteries, for instance, that we have, these little power banks, whatever, batteries in our phones, all of these things are usually made outside of the United States. Okay. Um, and of course, there's something that they call scale up that they're trying to do through this battery center. So yeah, maybe you can make um, some little demonstration of some battery technology that, yeah, it can actually hold more charge in that same volume, let's say, right? So then, yeah, I can cobble it together in my lab and make this little thing, right? But how can that be moved from there to an actual industry type prototype factory tool, and can it then replicate that, right? Because you got to be able to take what you've researched and now make it become commercial, right? And so the organization, if you're unaware, you may be international. This particular organization that's funded this, and like I said, I can't remember the exact number, but it's either 30 million or 40 million. They're all about our national security, right? So I'm apologizing in advance for some of what you might see here on this next slide. But as the way things are nowadays, right? No matter what country you kind of live in, things are just becoming more protective within your given country. Okay. So one of the reasons why these several reasons you see on the left-hand side, I won't go deep into, but it's clear that we're not making batteries in the United States. And that is perceived as a national security risk. Okay. So then this Beacons program or this Beacon Center, they're identifying or helping to fill gaps, as you see there, between the energy storage supply chain, so that there's a resilient supply chain in the U.S., right? So if it came down to it, and unfortunately or so terribly some kind of war breaks out or something, or some other pandemic happens, for instance, maybe that's more realistic. Having some form of pandemic, but then you're relying on raw materials, whether it's raw materials, whether it's some aspect of the manufacturing process that gets done overseas, then come back and gets finished up here in the US, or if, like I've just mentioned, pretty much the entire battery is made outside the country. And if there's a pandemic and everything shuts down, then no batteries can be made to come into the United States. So this is the kind of mindset and the why this center was created. So in addition to filling the gaps for, making sure you could theoretically start from raw material to finished product battery, and in identifying those gaps and helping to fix that, that's one role, obviously driving innovation. So this energy storage innovation, and simply that's what I was referring to earlier, right? Extending the life of the battery, let's say, or making it hold more charge, whatever. where we need to be part of that innovation. And then, of course, the workforce readiness that I mentioned, and then the demonstration, right? I'm university professor so-and-so, and I'm making those little coin batteries that go in like our key fobs in our cars or whatever, right? We can actually use that kind of a little battery to test out our battery materials. Okay. So that needs to be able to be scaled up if we find something really works really well, right? Because maybe you need to make a little power bank out of it now and things like this. So, and then can we replicate? It's on a smaller scale, I'll admit, right? I mean, we're not going to have some huge factory that's the size of four soccer fields, right? That then would, you would process and make all these batteries out. But we at least have little tools that replicate what a big manufacturing facility would actually have, so we can kind of help move the technology into commercialization and things like that. So here's a little bit of the details on that building. Just creates a great venue for battery research. If you notice there at the bottom, when you do this battery stuff, or like where they're made, the relative humidity in the room, because you have electrolytes and things, it has to be 1% or less, as you see on that second bullet. And this isn't just like some little tiny like glove box, right? This is like a room or a very large area, 35,000 square feet, so there's this is a really good capability to explore a lot of this battery business. Okay. So, with that, I'm gonna begin to transition into the academic programs. But before doing that, I wanted to show a video here of just it's kind of like, it's not necessarily the day in the life of a graduate student, but it's the students talking about the work that they do on the equipment that they use. Okay. So please, somebody let me know if the sound ultimately doesn't come through. I saw the setting in Zoom that I should have enabled that, but let's take a look here.
Hi, I'm Matthew Berschneider. I'm with Professor KJ Cho. It's a largely computational group, but we're expanding our capabilities over the last several years into actual battery material synthesis, testing, and optimization. So here we have the parameter, the equipment to synthesize the material, scale it up, in the glove box, argon filled, make half cells with lithium metal if we're studying cathodes or even anodes, and test the coin cells for long time cycling performance and even pushing the boundary of energy density.
Hello everyone, my name is Jia Yi. I'm a PhD student in Dr. Su's group. Dr. Su is doing research related to next generation energy storage battery. So what I'm doing is related to electrolyte. What you see me doing here is making a coin cell. Other team member in our group is doing research related to solid state batteries.
Yes.
And we are now
we can't hear anything on this side.
state-of-the-art
Okay.
Artificial intelligence to help us develop.
Let me stop, because in the share settings it said I could.
Chad, I could hear it, so
Okay.
I could hear the video.
I can also hear it properly. No problem.
Okay.
Okay, maybe it's just mine. I couldn't hear anything.
Okay.
Sure, sir. The sound is clear, but the video is delaying.
Okay. Okay. All right.
As for batteries.
Hi, my name is Chris. I work with Professor Amy Walker here at UTD in the Materials Science Department, and we do materials deposition, and we do this by photo-assisted chemical vapor deposition and chemical bath deposition. We also do some work on art restoration of historic artifacts. And right now you can see another one of our students, Tammy, who is in the process of getting the reactor ready for the next experiment, where right now he is removing the precursor holder.
My name is Jocelyn. I work with Dr. Rafiq Adu at UTD. And our lab mainly focuses on working with semiconductors, and we study the surfaces and interfaces of semiconductors. And we use mainly tools like X-ray photoelectron spectroscopy and scanning tunneling microscopy to study these surfaces. And we also do work with space coatings for satellites, and coatings that resist certain atomic oxygen effects.
Hello, I'm Dan Lee and I'm a postdoc.
Hello, myself Shovik De. I am a PhD student.
We're in Professor Ji Young Kim group. In Professor Ji Young Kim group, we're working on different material using atomic layer deposition technique. We focus on advanced materials such as dielectric material, metal oxide, and hybrid thin film for various applications such as MIM capacitor for memory and logic devices. We're also working on dry EUV photoresist material.
So currently I'm working on high temperature deposition plasma assisted boron nitride. This project is funded by NASA. So here we are trying to deposit boron nitride and tungsten nitride layer by layer atomic layer deposition for X-ray mirror application. So we have the system, that is plasma ALD and CVD system. Here I am loading, here two chamber is there, at high vacuum chamber and low block chamber. In low block chamber I am inserting the sample, loading the sample. After that we make it vacuum and transfer to the high vacuum chamber.
Hi, my name is Li Fang and I work with Professor Mu Kim's group. My supervisor, Professor Mu Kim, is a microscope expert, so I learn microscope with him. He gave me a lot of help for how to improve my skills, back knowledge about microscopes. And what we are working in our groups is, first I'm working on the scanning transmitter electron microscope, study of the gallium nitride high electron mobility transistors for the purpose of reliability. So it can enable us to do real-time analyzing and observation of whole device changing. And also we do collaborations with the industrial and academic, so help industrial to do some failure analysis and help the university to characterize some samples like a nanoparticle or something kind of this. So the tool what we used is this one. This is a microscope. This is an atomic resolution microscope. It's very good, so it can reach 0.8 angstrom resolution. So that means we can see atom position or atom arrangement of crystal materials. So for example, for this one, this is the silica 110 plane. So we can see the silica atom position like this. So that's a very wonderful equipment. I'm very interested in work on it. And so welcome to join our group, and you will experience a very wonderful nano world. Thank you.
I'm Nargol and I'm with Dr. Brenner's group. We do fabrication and characterization of 2D materials. So in order to characterize these materials, we use Raman spectroscopy to study the thermal properties of these materials. So what Raman does is that it shines the laser to the material, and most of the laser goes back, but some of it absorbs by the material. So what it does is it vibrates the atoms in the materials, and it isn't localized to one atom. It just spreads out to neighboring atoms. And this fact that the vibrational energy transfer between atoms is phonons. So we study the phonons, and for example, when we heat up the materials, we can see that the wavelength of the peaks changes because the material lattice is expanding, and so that it means that it's softening and the wavelength is shifting, and also the intensity decreases by raising the temperature, and it means that there are more phonons occupied. So in this case, we can study the heat dissipation in the material.
Hi, my name is Renan. I work with Professor Quevedo. In this group, we are working in some semiconductor material. In general, we work with perovskite, silicon devices, gallium nitride devices. Main application is for the harsh environment application in general for the material. We have many projects related with the memory store or memories. We have some projects related with the batteries, nuclear batteries in general. In principle, we are working different kind of semiconductor and try to find how these devices or this material has some defects or some electrical issues when you expose to the radiation. Radiation similar to particle or photon with high energy.
Hi, I'm Monet, and I'm with the Quevedo group, and we're a group that is a mix of chemists, material scientists, and engineers, and we specialize in materials for semiconductors. And now we're going to show you a little bit of our lab space and how some of the equipment for those applications work. Here's the XPS, and this particular instrument is used to determine the atomic composition of the materials that we work with. And here is the CSS, which is for closed space sublimation. And this system is really interesting because it produces some of the highest crystalline quality in perovskite materials in our field of research. And here's the probe station that we use to measure the electrical properties of the devices that we fabricate. And this is the Hall effect system that we have, and it's used to measure electrical properties of our materials, such as resistivity, mobility, and much more.
Hi, my name is Adam Glushetsky, and I'm a graduate researcher in Dr. Chadwin Young's research group. Our lab focuses primarily on electrical characterization as well as reliability testing, where we study the effects of electrical or thermal stress on semiconductor devices. My work typically begins by fabricating semiconductor devices down in the clean room. Once I have that completed, I'll come up here to the lab and load my samples into the probe station where I can make electrical contact with the devices. I then come to my semiconductor characterization system where I can select the proper test and configure any settings I need. After that's executed, I can extract data on various processing conditions on novel materials and devices.
Hi, my name is Sarah. My name is Pranay. We are both with Dr. Vandenberg's group. I work with designing optimized avalanche photodiodes. And I work on quantum transport modeling on 2D materials. In our work, we integrate Bayesian optimization, analytical calculation, and also TCAD simulation for designing optimized avalanche photodiodes. Other than TCAD simulations, we also build our own in-house transport codes. So we use our own codes to model and simulate devices. There are other people in our group who work on neuromorphic computing platforms, DFT calculations, and some others work on Bayesian optimization. There are also people working on FinFETs, and we have other students working on different dielectrics and also LDMOS, designing optimized LDMOS.
Hey. All right. So we will, like I said, continue on here so that hopefully we can get to some questions and things that you all may have. So I might speed through a lot of this because you may have heard very similar information in other programs or that you're finding out as you're attending some of the other sessions throughout this week. But at least in terms of kind of how our application process kind of works, these are the types of students that we look for. You can see on the left-hand side, as Shante had mentioned earlier, there may be things in the works to deal with the GRE. But as I understand right now, our department is still looks at the GRE scores. We request 3 letters of recommendation, a personal statement, and transcripts, which I think is pretty customary for anywhere you end up applying, whether it's another department here at UTD or elsewhere at another university. This is fairly standard practice, at least for the stuff on the right-hand side there. All right. The deadlines, hopefully you all can see things on the right-hand side there from the university's webpage. I just kind of tried to highlight a couple things here in the upper left with the priority deadline that's kind of shown there in the table on the right-hand side, and a regular deadline. And so, you can definitely reach out to us. There's some contact information I'll get to here on the last slide. These websites are obviously geared towards our graduate program in material science and engineering. We have our graduate advising requirements. If you click that link, it's like just a listing of the requirements of the degree, milestones, the pathway through the PhD and what you have to do, and things along those lines. The master's degree, at least in how things seem to work here, full-time students can usually finish that in about 2 years. Some of the required aspects of it, though, is that if you're part-time masters, you have to definitely finish it within 6 years. The master's degree can consist primarily of coursework, but there is the option to do a thesis. And that generally may add an additional semester's worth of time, potentially. Just depends on the level of the project and what kind of things are going on there. Because you're also asked, of course, write a thesis and then actually defend it once you are done with the work that you're proposing. Okay. The PhD in our department generally takes 4 to 5 years to do. And if you're part-time, you definitely have to finish that within 10 years. Okay. The 4 to 5 years, even sometimes, even if you have a master's, some of that time gets maybe you could do it in 3.5, because generally there's a semester kind of lost, maybe coming from another institution. And then, especially if you were in a different discipline than material science, like I said, with the uniqueness of our program, there might be some courses that need to be taken and things along those lines. So it could still take on average maybe 3.5 to 5 years if you're kind of coming in with the master's. But generally it's a 4 to 5 year time frame. And some students have even come from the bachelor's and got done in 4 years because they worked hard. They had a robust project that they could work on, and they worked hard to to ultimately get done in that time frame. All right. The components of the PhD and how it's outlined for us: we have the coursework. You're going to usually finish that in 2 to 3 years, depending on if you're kind of coming in with the master's. We do transfer some credit and things like that. I just didn't want to bog down this particular presentation with going over how that works, but we do allow students to transfer some credit in and things like that if you have graduate level courses. We do have a written qualifying exam in our department, and you get 2 chances essentially to take that. I do have, I think, a little bit of a little slide on that. And then, of course, as with any PhD degree, some level of research, whether it's experimental or modeling. As part of that, you would do a proposal defense, which usually happens within around the 3rd year. And then, of course, you'd write and ultimately defend a dissertation at the end. Okay. So this is probably something that's a little bit more relevant to what you're interested in. Our department divides courses into 3 categories. We have what we call our core courses, and that's our foundational material science and engineering type classes as it relates to us being in this nano electronic material focused kind of infrastructure, for lack of better words, here at UTD. So then from there, you have various advanced classes, and then there are some elective courses that you could take, and they're often, very special topic or have a very narrow scope in what they cover. They'll drill down a little deeper, right? That's why you're in graduate school, so you can drill down a little deeper. All right, but the courses below in green are what we call our core courses. All right. If you maybe don't have a material science background, you will be advised to take the Material Science 5300, the Intro to Material Science. Then we go into thermo, materials characterization, quantum, and electrical, optical, and magnetic properties of materials. So with that being said, then, for the master's degree, it requires 30, minimum of 30 total semester credit hours. The 4 core courses are required as part of those 30 hours, and then 3 advanced courses with at least 1 in a classical material science type of class. Again, I didn't put all our whole listing of classes here for the sake of time and seeing as how I'm going as long as I am anyway, and we're close to ending. I just didn't put all that in here. Then you can also take up to 9 hours of research, wherein if you do the MS option, the master's thesis option, you have to have a minimum of 3 hours of material science research for the thesis, which is that labeled class that you see there. All right, now what I will say is we are going through the voting process, and I'm thinking that it is highly probable it will be successful in the coming fall of 2026. That 4 core course requirement will drop to 6. I'm sorry, drop to 6. It'll drop to 2, and then it gives a little bit more flexibility and maybe even allows you to take a class. Say you wanted something in entrepreneurship out of the business school. You could, for instance, go take that and things along those lines. Okay. The PhD degree, you see it has a 75 minimum. The maximum is 100 hours. So they actually discourage, going much over the 100 hours. The 4 core courses are required, like I said, in this case, though, because the qualifying exam is based on that. All right. So the key here, though, is if you're a master's student and you're considering the PhD, or maybe you get admitted to the master's program, but not the PhD program, but you still at the end of the day maybe want a PhD, it'd still be in your best interest to take the 4 core courses, because that's and you're allowed as a master's student, if you notify the faculty member ahead of time that you want to take the qualifier, just in case, to leave your options open. You have to let them know kind of at the beginning of the semester, and then they'll make sure you're on the list to be able to take those qualifying exams. All right. Yes, I think we pretty much did this one already. All right. So yeah, this is our change that I was talking about. So now you could, hopefully this is, like I said, it's pretty, I think we have the buy-in from the faculty. We just have to have our formal vote at the next faculty meeting, and then it has to jump through a bunch of university hurdles to get final approval. But then, yeah, you could take 2 of the 4 core classes and take at least 24. That's SCH, stands for semester credit hour, of MSCN numbered courses. If you do the thesis, then you get the 9 hours of research. All right, including the thesis. Okay. All right. One other thing that we do at least around twice a month is have colloquium speakers come, and basically they're seminars, and it just exposes you to, as hopefully, like with a PhD, you become very focused, say, in a semiconductor device type technology. Well, you saw that we do battery technology, that we do photovoltaics, we do perovskites, and optical materials and different things like that. Well, we'll bring in a bunch of different speakers, but it could be faculty colleagues at some other university. It could be other people from industry or what have you. But bottom line is it happens about every couple of weeks. And the students are expected to attend and be present, and we take attendance and, things like that. The other thing that happens maybe on those off weeks from when we have the colloquium is sometimes there's a student seminar series, and us as faculty, we're put in a rotation, and whenever our name pops up, maybe a couple of months out, we know that one of the students in the group should go and present their work of what they're working on to this point to their peers. It gives them practice with presentation in a not as nervous of an environment of like being at a conference and giving your first oral talk or what have you and things. This would be the best platform because the students are genuinely trying to learn and learn more about what you're doing, and things like that. Sometimes we're in person or we might be on Teams. And then if we're in person, we usually have some kind of refreshments available at the beginning. Okay. So I know we're getting a little over time here. I think a lot of this is pretty straightforward. I do want to spend time on this slide. All right. That is our qualifying exam. Remember, there's these four core classes. So what happens is you will take two of them in a given fall semester and then the other two in the spring semester. At the conclusion of the fall semester, for instance, after the holiday break, but before the spring semester starts, so this generally means early January, you'll take the first two sections of the fall core courses, the two courses, I think it's generally thermo and quantum mechanics. Those two, you'll take two tests in that beginning of January window. Then you'll hopefully pass and all that kind of good stuff. And then through the spring, you'll take the other two classes and repeat the same thing like in late May, early June. Okay. All right. Now, here's one thing that's critically important to students for you all to know potentially is that if you do make an A in the course, you will be exempt from having to take the qualifying exam. So that's just one incentive to try to do well as best you can. All right. All right. So with that, we've got only a couple more here. I think I won't belabor this point other than we're going to talk about some funding because generally you all as students really want to know what kind of funding opportunities we have through this North Texas Semiconductor Institute that I was just talking about. They have received funding through this workforce development aspect to do a master's program that is fully funded. Generally at UTD, our master's programs are not fully, we don't necessarily fully fund a student. And most master students are having to pay out of pocket. Well, this is an opportunity if you're just interested in the master's or want the master's and continue to the PhD, but it might be difficult to find a faculty member that has funding at the time. This is a potential option. And you can be at UTD, you can either be in material science and engineering, electrical engineering, or accepted into mechanical, right? So any of these three disciplines, this will start next fall. I have a QR code that'll come up here in a second. You get full paid tuition for the 4 semesters, and you get a stipend for living expenses or being able to, at least with a roommate, you should be able to live off of the stipend for 5 full semesters. So that includes the summer, so that you're funded in that, master's, like I said, usually takes 2 years. In that summer, that's what that funding also helps cover, is those months in the summer. Okay. The requirements are to be a U.S. citizen or a U.S. permanent resident, and you need to hold a bachelor's degree in the physical sciences, and then of course kind of be accepted into one of those 3 master's degree programs, whether it's material science, electrical engineering, or mechanical engineering. All right. This is the typical requirement thing in terms of the GPA, the usual application, just like any other scholarship. Of course, you're competing for one of these 10 slots. So you're going to have to put the best foot forward and things along those lines. The other requirement is that you actually complete the graduate certificate in semiconductor technology that I alluded to earlier. What I want you all to know and understand, it is still very easy to get that certificate, even as a master's student, because the courses that you would maybe take as electives and different things, they're a part of the list because we're a more semiconductor or nano electronic material focused department, right? So in addition to that, you would have to complete the master's thesis on a semiconductor technology related topic. Okay, those are the major requirements. Like I said, I won't belabor this point here, but the certificate is, it requires 12 semester credit hours, which is the equivalent of basically taking 4 classes. So you would have to take the required class of electrical, optical, and magnetic properties of materials. Then you would choose one of these 2 classes. And then there's these host of other classes that are related to semiconductors, even like a materials characterization that you see right there, right? I mean, it's just, I mean, TEMs are at these chip manufacturers, for instance. So somebody knows of microscopy, you know, and things along those lines, or there's heat dissipation, all in packaged parts. And while your laptop gets hot, we need to understand heat and things. So, you know, and lastly, you can even petition for a particular class to be accepted. And it would come to me and you'd have to show and prove to me how it was relevant to semiconductors. And then I can improve it even if it's not on the list. All right. So I'll pause here for a second because we only have a couple more slides after this one, for you to maybe capture this QR code if you're interested in that. It'll take you directly to that particular website. And I'll obviously get with Shantae these PDF, these slides or whatever, and find out whatever mechanism you all can access them. And so make sure they're placed wherever they need to be so you all can access them. All right. And since we're on the topic of graduate funding, this is just the different types of funding offered here at UTD. Some are for students who are currently here. You know, if you tried to apply and you hadn't fully started yet, you're going to be competing against the students who are already here. So, you know, if it's even allowed to apply early, at least in this Jonsson School Dean's graduate scholarships, the ones that we have that are designed specifically for new students are located here in the middle, right? This Eric Jonsson Fellowship in Material Science and Engineering. So this is for newly admitted PhD students into our PhD program. Okay. You got to
Professor
be full-time.
Ivan, I
Yes.
have a question.
Yes.
First of all, I'm very thankful for all the helpful information. My name is Sahim, a partner, and I'm interested in applying for a master's program at the University of Texas at Dallas. I request for clarification regarding the GPA evolution process for my admission eligibility. I have completed my Bachelor's of Computer Science degree at the Nangarhar University, Afghanistan, under the Faculty of Computer Science Department of Software Engineering. The official transcript issued by the university indicates a cumulative GPA of 2.5. However, prior to my admission to the Nangarhar University, I completed 2 academic years at the Nangarhar Mechanical Institute, which operates under the Technical and Vocational Education and Training Authority. This institute's transcript also attached reflect higher academic performance that contributed to my overall education before transferring to the university. According to the official note on my university transcript, my first 2 years of study at Nangarhar Mechanical Institute were accepted by and credited toward my BCS degree program through a special examination process named Concord. Therefore, I would like to kindly ask whether these 2 years of credited coursework can be considered in the GPA calculation for admission purposes. If they are included, my cumulative GPA may exceed the 3.0 threshold required for graduate admission consideration. I hope you got the picture.
Yes, I think I understand. Maybe Jackie, just Dr. Harris here, if she can maybe comment. But what I would think I would do if I was in your shoes is I would, of course, when you upload the transcript, I think it's just an upload of a file. So I would have all of that stuff in the proof of the grades and all of that as kind of like a transcript thing. But then in your personal statement, at the very beginning of that personal statement, you should be explaining all of what you just told me. Right, because then it makes then anybody reviewing your application can understand. They can understand what the packet is of all the transcript information and things like that. So I hope that kind of makes sense.
Yes, I agree with Dr. Young. If you can submit your unofficial transcript up until you first start classes, we can still submit that to the admission committee to review. And yeah, putting in your personal statement, your challenges, your struggles, all that is very important for the admission committee to know. That way it can help you be a better candidate. So yeah, I agree with what Dr. Young is saying. But yeah, if you can submit an unofficial transcript, that would also help.
Thank you. Thank you very much. I understand.
Sure. All right. And then my last slide here is just the advising email address. So that's one that's generally sometimes for the students here, but we also kind of use it for helping with admissions and things along those lines as well. Okay.
Yes, we do have a MSc admissions at UT Dallas at the
Okay.
EDU, but that is currently being forwarded to the MSc advising. So we'll also see those emails as well.
Okay. And I guess with that, I'll show this last slide as our social media platforms that we're on and open things up for questions. If it's okay with Shantae, since I've ran past time, I'm willing to still be here and answer any questions you have.
Yes, that's definitely fine. Thank you so much, Dr. Young, for sharing all this information with our students and also including funding, because that's such an important concern for our students. So students, if you have any additional questions, please feel free to unmute, or if you want to pop them into the chat, Dr. Young or Jackie will be, I'm sure, happy to help answer those.
Ma'am, I just missed the others meeting. So where can I find the recorded meeting?
Yes, for sure. So I'm going to pop that into the chat. So this meeting will appear. It takes it won't show up right away. It'll be sometime this afternoon, but you can find it on our YouTube channel at UT Dallas or UTD, sorry, Jonsson grad. So if you just go to YouTube and punch that in, you'll see the past videos from this week, as well as the morning one hasn't been posted yet. Both of those will be posted sometime after 1 p.m. once the recordings upload, but they'll be posted this afternoon and moving forward. So that's where you can find them.
Thank you very much. Thank you.
You're welcome. Any other questions before we end our session today? All right, excellent.
All right.
Well, you can definitely reach out to me. Dr. Young, did you put your email? You had your contact information, right? Or if you want to pop that into the chat, maybe for the students.
Yes.
So students, thank you so much again for taking time out of your morning or possibly evening, depending on where you're visiting us from, to attend the information session today. We really appreciate it. If you want a copy of this presentation, send me an email or send Dr. Young an email, and I'm sure he'll share it with you. Otherwise, the recording for this session will be posted on the YouTube channel. Then you can watch it as many times as you want. Press pause to definitely get a hold of some of that funding information. We look forward to seeing you the rest of the week. Tomorrow morning at 9 a.m. we will be hosting our international session, and then at 10:30 we'll be hosting the Office of Graduate Education session. So thanks again so much for joining us today, and you guys have a great rest of your day. Bye.
Thank you. All right, bye-bye.
Thank you very much.